be wearing my mask. But if you don't feel comfortable or risk group or whatnot, or if you want to take a nap, just feel free to leave and all that. Without further ado, my lecture will be on the Blackboard. And I think it only works if you folks ask questions. So just interrupt me at any time. I can take questions in any languages. I just don't guarantee what I'm going to answer. So let me know if you cannot see my handwriting. I know that this is a little bit too small. I'll try to make it a little bit larger. So what I'll try to do in these next lectures is to give you a broad overview of neutrino oscillation physics. I'll also talk about how to produce and detect neutrinos. And if time allows, I'll talk about cosmogenic neutrinos and maybe some advanced topics, but who knows. All right, so let's start with neutrino oscillations. Let me know if you can read this. Okay? So, when you produce a neutrino, quantum mechanics 101, your neutrino is your flavor neutrino, which is defined as the neutrino you produce, is a combination of mass eigenstates, which are particles with a well-defined mass. So I will try not to call the flavor neutrinos particles. I think particles should have a mass. At least this is my own personal definition. But when you produce a neutrino flavor alpha, this guy is a sum of some coefficients. There's a star here for some reason of these guys, and these guys have mass mi, okay, well-defined mass. The reason for this star here, you would typically not write with a star, right? This is what we call a PMNS matrix. Pontecorvo, Maki, Nakagawa, Sakata, I guess. It's being recorded, right? So the reason why there's a star here, like if you just write this equation to start with, you don't write the star, right? The reason why I have the complex conjugate is just because if you write this for fields, you write as this. Let me do like this. Nu alpha, U alpha I, nu I. You write like that, but remember, this field annihilates neutrinos. So to write the state, you need to apply the dagger on the vacuum. And because of that, your U becomes a U star, okay? So that's the reason why there's a star there. It's not because we are dumb. I mean, that doesn't exclude the possibility that we are dumb. So when you produce a neutrino alpha, and you want it to propagate so that you detect the neutrino beta, you calculate this amplitude by simply doing, you detect neutrino beta, you produce neutrino alpha, and in the middle you just let the state evolve, and as you know well, the evolution of the state is given by the Hamiltonian. One small thing, we're going to work with this. Does anybody never saw this? You're good with that? If you have any concerns about it, let me know. I can make it very clear what is what. But essentially, you time evolve, but you know, L equals T because C equals 1. So if we just work this out, we can open up nu A and nu beta like this, and we'll get something that goes like, there's a sum in ij, nu j, u beta j, ihl, u alpha I, nu I. This is an eigenstate of the free Hamiltonian. So this is just the energy of this state, okay? And now when you apply this to that, it's just energy. These are just numbers. They all come out. And then nu j, nu I is a delta ij. That gives you u beta j u alpha j star exponential ejl. And if you see here, I'm actually doing implicit sums. If I have the same index, I'm summing it, okay? Implicit sum, all right? Because I really don't want to be writing this over and over and over. So the energy of a neutrino, as we know, goes like this. Experimentally, we know that the mass of the neutrino is very, very small. We can get there at some point. So we can approximate this energy by energy of neutrino J equals the momenta plus the mass over 2p, okay? This is a little bit of cutting a corner. There is something more to it than that, but we're not going to go there, all right? In a nutshell, I'm saying that when I produce a neutrino alpha, which is a combination of neutrino 1, 2, and 3, for example, I'm saying that the energy of neutrino, say 2, is a momenta plus the mass of this neutrino over something. 3 momenta, blah, blah, blah. So I'm saying that the momenta is the same for the 3 neutrinos. That can't be true. If you just work out kinematics, that just can't be true. It is true to a very good approximation. So energy momentum is approximately conserved because I'm approximating my expressions here, okay? So now, we can put this back here. We know from quantum mechanics that whenever we calculate observables, overall phases do not really matter, right? Because you're going to modulus square something. So this guy here doesn't matter. So when I put it back here, I have an amplitude of neutrino alpha going to neutrino beta that goes like, there's a phase which I'm not going to write, u beta j, u alpha j star exponential, maybe I should write like this, of minus I m j square over 2 E L. And I just did something there that I said that P is equal to E. You know, if I just expand this one more step with another expression for E, this is going to be fine. And approximately P is equal to E. So this is what people usually do for oscillation physics. It is a bit sketchy. It feels wrong because of energy momentum conservation, but it's approximately right, okay? So now, what you do is you say that the probability of producing neutrino alpha and detecting neutrino beta is the amplitude square, okay? And you can show, oh, by the way, my notes, my handwritten notes are available. I don't know if you have them already, but if you want them, I can just email to you. They'll be on the school website at some point. I also have like an exercise list for the hands-on or tutorial something that we're going to have. You don't need to solve all the exercises. I think they're all fun, allegedly. Hopefully, you will have fun when solving them, but the goal is that all the exercises there, they're like, if you're a neutrino physicist, you need to have done all these exercises at least once in your life-ish. So one of the exercises actually to derive the formula that I'm going to write here is a very simple one, but you can show that the probability of producing neutrino alpha detecting neutrino beta goes like this. There's a 4 here, sum. I'm putting the sum back because the sum has this non-trivial relation, u alpha, alpha, beta, beta, I, j. J, oh, that's wrong. I, j, star, star. I guess this is right, or it's a real, it doesn't matter. And then sine square delta m square ij L over 4e plus 2 times the imaginary part, and I forgot the sum in my lectures, my lecture notes. There will be typos in my lecture notes. If you find them, just shoot me an email, please. I can update them easily. I guess I can just repeat this guy here. Alpha I, alpha j, beta I, beta j. Let me make sure that the stars are in the right place. And then sine of delta m square ij L over 2e. All right, so this is the general neutrino oscillation formula. Written like that is not super duper useful. Go ahead. You are right. Yes, thank you. Written like that, at least, okay, so there are many kinds of theorists, and you'll see some different theorists around. Like you saw Graciela, you see me, you see Mateus. Different kinds of theorists behave differently. We are like different species of animals, every one of us. I'm the kind that looks at this and I say that this is useless to me because I like to know numbers and I want to see something that I can understand. And honestly, one of the things that you should be trying to learn here is which kind of theorist, if you're a theorist or experimentalist, you are. Like, what is a useful expression for you? Is this real useful because it's super general? Maybe. It's not to me. To me, what is real useful is something that I can hit my eye and understand. So let's take a simplified system of 2 neutrinos only, okay? Where the mixing can be given by just one angle, so nu E and mu written as nu1 and nu2. Now I can actually write these u's here as a function of these guys, and this we can have, for example, the probability of, let me write this, nu mu going to a nu e as sine square 2 theta sine square delta m square L over 4e. Okay? So that's telling you the following. If we only had 2 neutrinos in nature, we have 3, which makes life more interesting. But if we had 2, a mu neutrino becomes an electron neutrino with an amplitude sine square of 2 theta, which is the mixing, with this phase, okay? Now this actually, it's a very useful formula, although it's only for 2 neutrinos. It's still not super useful to me because I want numbers for this thing. So we can write this as 1.27 delta m square in EV square, distance in kilometers, and the energy in GeV. If we just plug in numbers, it comes out like that. So let's take a second to understand what this means. Experimentally, we have measured that the delta m square, the mass splitting, let's say, between neutrino 3 and 1, at least the models of it, we don't really know the sign, is about 2.5 10 to the minus 3 electron volt square, all right? So if we plug in numbers, for 1 GeV neutrino, it will take like order 1,000 kilometers for this thing to oscillate. So these numbers, although they may sound just as numbers if this is your first encounter with neutrinos, they actually define the field, right? It's like, I can't really do neutrino oscillation physics on a tabletop experiment. It just doesn't work. I don't have distance. This system takes like kind of forever to evolve. So you need to build up your experiment such that you start, say, at Fermilab with a neutrino beam at Fermilab, and your detector is at 1,000 kilometers later. Now, if you think how much you lose when you go 1,000 kilometers away, right? Fluxes fall like 1 over radius square. So in some sense, it's actually a bit unfortunate that these mass splittings are actually so small. If they were larger, we might be able to do experiments, between the IFT and USP. If you do that, it's like 0 distance, essentially, right? If I put an L here of 1 kilometer, I lose a factor of 1,000 in this phase. Sine square, you actually lose a 10 to the 6. So that's life, right? Any questions up to here? All right. Oh, yeah, go ahead. Where? Here? No, there's no delta here, right? Oh, sorry, it's a capital delta, yes. Capital delta m square, yes. It's just because this guy here, ij, is defined as mass I minus mass j, okay? Square. All right, cool. There is one step that I kind of hid here, which I said to you that this mixing can be parameterized by a single single angle. But in principle, you could put phases here, right? So why don't you? And the reason is because you can show that these phases are unphysical. That's a great question. The way I'm doing this, I'm calculating at the laboratory frame, but it doesn't need to be. You can do at the neutrino rest frame. The only thing is that the neutrino rest frame is going to be like a very weird rest frame, right? So basically, neutrinos live for what? Live. Neutrinos take about, to go like a kilometer, what, 2 milliseconds-ish? So they're almost at the speed of light. The rest frame is, there's no rest frame if you're a photon, but you are like as close to a photon as you can be being a neutrino, right? I guess you could calculate this on the neutrino rest frame. Probabilities should be invariant. But now you need to relate the baseline with the self-time, right? The time that the neutrino feels in its own rest frame. Yes, yes. So essentially, if you calculate on the neutrino rest frame, if you calculate the relation between this distance and the time it takes for the neutrino in its rest frame to oscillate, there will be some gamma factors of E over m, which will be very, very, very large numbers, right? But yeah, you can calculate on the neutrino rest frame if you want. I did not. I just said I produced a neutrino. I produced in the laboratory frame because I'm at the lab. But I'm cheating here, right? I'm just like justifying something that I didn't say. But yeah. So yeah, like the most useful way to do this is to do in a way that experimentally can be measured. If you do a calculation you want to relate to experiments, again, that's the kind of theorist I am. And I can only relate to the experiment if I go to lab frame. So I don't even ask myself what frame I should do. I always do things in the lab frame if this is what experimentalists will measure. Yes. Yes. That's a problem. Because each neutrino technically will have different momenta. You can see that very simply by saying, well, now I'm not going experiment anymore, I'm going theory. Let's go in a pion rest frame. So I have a pion rest frame here. And my pion decay to a muon and a muon neutrino, which is the sum of this, right? Where there's an implicit sum here. If you calculate the kinematics, you can actually do it by hand very easily because it's a 1 to 2 decay. You see that the energy of each neutrino, the momentum of each neutrino, and their mass are all different. So in reality, this formula only works because what happens is that pions can never really be at rest. There is a wave packet for the pions, right? Which means that there is a spread in the energy and momenta of each neutrino, and they overlap. If they do not overlap, you don't get oscillations, right? Calculating the wave packet is a mess, but that's a detail. All right, so any further questions? Okay, so on this guy here, I told you that you could put phases there. There is an argument from QFT that you can rephase things away. I'm not going to go there because I don't know if everybody saw QFT, but I can actually give you another argument, which is the following. The phase on the PMNS matrix is related to the violation of CP, of charge parity, okay? And you can see that by the fact that when you, maybe I should write it here to be more clear. Yes. This field, and I told you I wasn't going to talk about QFT, but this is like baby QFT. This field creates a neutrino. It has a U star on it, okay? But if I want to create an antineutrino, I use the psi field. This guy here creates a neutrino. This guy here creates an antineutrino. This guy here has U instead of U star, okay? Which means that the phase of the PMNS matrix distinguishes neutrinos from antineutrinos, and this is CP violation. When you have two neutrinos only, there is a very cute argument which does the following. If I want to look at this kind of oscillation, and I do a CP transformation on it, CP changes neutrino to antineutrinos, you get this. But if I actually do a CPT transformation on it, it changes neutrino to antineutrinos, and it flips because of time, CPT. But actually, it's still the same. Now, CPT is a very, very, very important symmetry of physics. If you look, again, in QFT, without CPT conservation, charge parity and time reversion, without that, you actually get probabilities which are not bound to be between 0 and 1. So I don't even know if you can call that probabilities anymore. You get negative norm states, which I don't know what that exactly means experimentally. So we rather keep CPT, okay? And CPT tells you that this is equal to that, which means that these probabilities are the same. But CP also says that this is equal to that. So there is no CP violation. There cannot be CP violation in this observable. Now, if you take this, you can CP to the bars. You can CPT to the bars, flipping the initial and final state. And you could even like T to this. And, well, you can CP to that, whatever. Now, why don't you have CP violation with two neutrinos? Well, with two neutrinos, we know that when you produce a mu neutrino and you oscillate it to a mu neutrino or to an electron neutrino, well, these are all neutrinos there is for a two neutrino framework, the sum of probabilities is 1. Same is true for antineutrinos. I'll just do bars here, okay? Hopefully that is understandable. But now we said that this guy here, where is that? This guy here, I should do a different color, is the same as this guy there because of CPT, okay? So we can write this equation as P mu mu, P mu bar E bar equals 1. And now I can write this P mu mu using this equation. I should go here. And we get P, so mu mu is 1 minus that. So 1 minus P mu E plus P mu bar E bar equals 1, which means that P mu E equals P mu bar E bar. Let's take a step back. What are we doing here? There is no way to show from just CP and CPT alone that there is no CP violation in two neutrinos. But when you assume that probabilities are summed up to 1, which is quite reasonable, you actually get that your nu to nu E oscillation is identical to nu bar to nu E bar. So that is a physics argument of why we have no CP violation in two neutrinos, so there's no need to write any phase there. If you know QFT, you could actually just rephase the fields and see that you can eat up all the phases that show up here, no matter how many you put there, okay? Here. So the argument is, for two neutrinos, nu mu's oscillating, so nu mu disappearance, that's what we call this, and nu mu bar disappearance are identical because of CPT invariance. Now, because I only have two neutrinos, my probability equations are actually very simple. I have this plus that equals 1, this plus that equals 1. If I just substitute this probability here, I get that the nu mu to nu E probability is identical to the nu mu bar to nu E bar probability. If I had one more neutrino, like in the standard model, say tau neutrinos, then I would have another guy here, plus P mu tau. I would have plus P mu tau for antineutrinos. And if I try to put it back there, I will actually have more probabilities here. And then this thing will have more dot, dot, dot. So with more neutrinos, you cannot prove this, which means with more than two neutrinos, you will get, like in general, CP violation. But with two neutrinos, because the system is kind of very simple, these equations have very few parameters. You can actually show like this, right, that you don't get CP violation. All right, cool.
I have a very naive question.
That's fine. There's no naive question.
So I'm just a little bit confused because you said that this is what you can show for two neutrinos.
Yes.
Now, are you saying that in 3 it still exists, but it's harder to show?
No, 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 no. This is a great question. At 3, for three neutrinos, and I'll write so we are very clear, P mu E in general is different from P mu bar E bar. They could be the same if there is no CP violation, which you need to put that by hand, right? You need to say, God told me that there is no CP violation, boom, that's it. But if there is CP violation, and in general there should be, these oscillation probabilities should be different for three neutrinos or more. So the point is, for two neutrinos, there cannot be CP violation. For more than two neutrinos, there can always be CP violation.
And why is that important?
Oh, because, so there are two things. One is that, okay, so one is not why is it important. It is what it is. If you think that you are measuring your neutrino oscillation parameters by looking at neutrino, let's say, nu mu to nu E appearance, there is actually way more parameters there than one single observable, right? So like you have one observable, you have more parameters. You might need to measure as well this oscillation on nu mu bar to nu E bar. That's just what it is. In principle, okay, I'll say that, but it's a very hand-wavy argument. If there's no funny business in the universe, matter and antimatter will just annihilate itself. We are not here. For matter to dominate over antimatter, one of the conditions that you need to have, which is called the Sakharov conditions, is CP violation. This is a logically true statement. That CP violation may have absolutely nothing to do with the amount of CP violation you need to have in the early universe, And in general, it actually does not have anything to do. But it is a source of CP violation. So,
I didn't understand why was it important. So, you know, like why does it matter to it? Like what would it imply in the rest of, in the big picture?
yeah, so let me keep going, which the CP violation will be actually way more interesting later. So for three neutrinos, are there more questions? Okay, cool. How much time do I still have? Oh, I have lots of time. All right, so in our next 2 hours, maybe I can erase this. So for three neutrinos, which is actually what we have, you cannot prove this, actually. There's more stuff here. But, and the expressions will get super long and all that. I'm not going to go there. But for three neutrinos, what you need to know is that the PMNS matrix is written as a product of three rotation matrices. This one here, 0, 0, 0, 0. This one here, and you can see here your phase, okay? This is just a parameterization. S12, S12, C12. And there is actually one more thing that shows up here, which I may not have time to talk about it. Oops, that can't be a 0. So this is called a atmospheric mixing, reactor mixing, solar mixing, and the Majorana phases. The reason for these names is related to how we discovered things or how we measure things. Again, this is just a parameterization. You're free to use whatever parameterization you want, but don't, okay? Everybody uses that. If you change that, you'd rather have a very, very good reason for changing that, okay? It's like getting here and speaking a different language. Things that depend on parameterization, they are not super duper physical, but they're extremely useful for us to communicate. So if you can, do not change that. Always use this parameterization, all right? The Majorana phase is a little bit different, is a little bit delicate. For us, it's not going to show up in oscillation physics. The reason is, I think I erased it, but yeah, I did erase. If you take the expressions for the probabilities, you can see that they all disappear from the oscillation probability. Mateus may talk more about them, because Mateus is going to talk about neutrino mass models. But if we have time, we can actually cover that by the end of it, okay? All right, so let me tell you now about something that is actually super important for neutrino oscillations, which is called matter effects. So what are matter effects? Matter effects happen when neutrinos traverse matter. If you think about it, neutrinos feel the weak interaction. Matter is not neutral regarding weak interaction because weak interaction is broken, right? So there is actually an overall weak charge of matter, which is actually ginormous, right? Because in every gram, we have about 10 to the 24 protons, neutrons, and electrons. So if you sum up proton, neutrons, and electrons, if you sum up their a weak charge, this thing doesn't cancel to 0. So the weak charge of matter is enormous, which means that when neutrinos are propagating through a dense media, they'll feel that. And because they feel that, what matter does is that it changes this slightly. It changes slightly the neutrino dispersion relation, okay? There is an exercise to derive the matter effects for real, like without cutting corners. It's not what I'm going to do here. I'm going to cut lots of corners, okay? And the reason why is that it's a long calculation, and you got to know QFT. But you know, if you follow that reference over there, you can actually do that. I hope you do that at some point. But here's the deal. When neutrinos are propagating through matter, let me, for now, just consider electrons. It fills the electrons via two diagrams. Make it larger. One with a Z exchange and one with a W exchange, the weak bosons. And this introduces a new term in your Lagrangian. So here are the corners that I'm going to cut, and I'll tell you how you get to the matter effect. If you want more details, go to the exercise, and we can talk about in the afternoon. So first, what you do here is that you write your Lagrangian. Honestly, in 90% of life, you always start by writing the Lagrangian, right? Now, you integrate out the W and the Z. So what does that mean? That means that the W and the Z, they are very heavy. Well, there's no such thing as very heavy, right? Any dimension-full statement needs to be compared with another dimension. So the mass of the W and the Z are very heavy compared to neutrino energies or the momentum transfer in this diagram, okay? That's what I mean heavy. So you don't really see the W and the Z, so you can just integrate them out. If you never integrated something out, the way to do it is that you derive the equation of motion for that particle. You set the derivatives of that to 0 so that it doesn't propagate anymore, and you expand in large mass, okay? We can do that in the afternoon if anybody's interested in deriving this for real. This will give you something like an effective Lagrangian, which goes like this. I think this is correct, including the factors of 2. Can you still see this here from like the corner? It's good? All right. And then there is this guy, P left nu E gamma mu P left E dot dot dot. This is the diagram we get from this, and there's other diagrams with the Z and like protons, neutrons, etc. There's one step here that I skipped. Again, you gotta use fierce identities to like shift fields around. Remember that some of these fields are fermions, so they might get a minus sign, and so on and so forth. And then you trace over the background. What does that mean? Tracing over the background essentially tells you that you are applying your Lagrangian term, which essentially is going to measure like how much matter is affecting the system. You're applying that to a dense media. So you're doing this. This is the background. Then you have your operator, which I'll just write as O. Maybe I shouldn't. G 2MW nu E and saying that you do the trace, you are doing that for maybe I should do that's fine, for a distribution of electron momenta. Okay? So you're basically seeing how this operator acts on every single electron of your background. If you just follow the computation, remember that E bar gamma 0 E is E dagger gamma 0 E, which is E dagger E, which when you apply to a background, that is just the number density operator, okay? This annihilates an electron. This creates an electron. So this just counts the number of electrons you have in your background. And this guy here is coupling to the spin of the electron. It doesn't really matter as long as the background is isotropic. So when you integrate, do the average, etc., that actually goes to 0. So after doing all that, this is still at the level of a Lagrangian. You can write an effective operator, sorry, an effective Lagrangian that will have the, this stuff like D, let me just write, nu, D, nu, for all neutrinos. But then there is a new term, dot, 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 and then there's a new term from this integral, which is something that goes like this. G Fermi, nu, gamma 0, nu. And if you think about it, remember, the way that we know what to do with Lagrangians is by equations of motion, okay? So you always go back to equations of motion. When you derive the equation of motion for the neutrino, there will be a term that will go like this. And this term will give you something like root 2 G Fermi dot, dot, dot. This, you have gamma 0 dt dot, 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 plus that. This guy here is gamma 0 energy. So I apologize for that being a little bit sketchy and maybe a little bit advanced. If you follow here, you can actually see all the details on this calculation. But the point is, the reason why we call that a matter potential is that the gamma 0 here has the same structure as the thing that accompanies energy. So this is why we call it potential, right? This makes your dispersion relation like this. P squared plus M squared. Whew. All right. So why do we actually care? Where V is 2 root 2 G Fermi electron density. All right, so let's take a step back. So the first thing I told you is that I'm going to do only electrons for, simplicity. It actually turns out that if you add neutrons, protons to this thing, you can add them here. The Z boson does not distinguish the flavor of the neutrino. The matter potential that is induced by electrons, neutrons, and protons via the Z boson is the same for all neutrinos, which actually does not affect oscillation physics. It acts like an overall phase, so you don't really need to calculate that. Although if you do all this calculation, just changing by electrons, neutrons, and protons is going to be trivial. So this is actually the only part of the potential. I think there's an extra 2 here. Should be like this. This is the only part of the matter potential that really matters, and it only applies to electron neutrinos. Because if you put a muon neutrino here, the background has electrons. If you put a muon neutrino here, you need to end up with a muon that is not, when you do the trace over the background, that will be a 0, okay? So one of the exercises to derive this for real, but let's go back to our philosophy of plugging in numbers. Let's see how big is this effect, okay? Honestly, at least, again, this is the type of theorist I am. Every time you calculate something, you got to plug in numbers to see what is the size of that. So the matter potential is, if I just put this thing is root 2. Then there is G Fermi, which is about 10 to the minus 5 GeV to the minus 2. Maybe there's a 1.1 here, but I don't think I really care. Maybe I do. 1.1. And then the electron density, let's just say 1 gram per centimeter cube of, I don't know, something that has the same number of protons and neutrons. So it's about 1 Avogadro number per centimeter cube. So let's just say 6, 10 to the 23 per centimeter cube. These numbers not really tell me much, so what I need to do is to multiply this by h bar c to the cube, where h bar c, I can do that because h bar c is 1, right? H bar c is about 200 MeV femtometer. If you multiply that here, you get 8 10 to the minus 14 electron volts. Now, very soon on neutrino physics, you realize that orders of magnitude will be like big. You have easily like factors of 10 to the 10 here, 10 to the minus 10 over there. It's actually pretty annoying. But the nice thing is that if you make a mistake, you'll be like 10 orders of magnitude wrong, so that's easy to spot. Now, this is small. This is super tiny, okay? Why does that actually matter? If you look at the delta M squared, the mass splitting for, say, atmospheric neutrinos, and let's take a root of that because it's mass square, this is about 0.08 electron volts. So how can it be that this actually matters over that? The reason is, if you go back to our oscillation formula, remember that that phase of the evolution operator, that exponential of minus IEL, that exponential actually had a term which went, and that's a term that is relevant, delta M square L over E. So the quantity that is actually relevant for this is not the root of delta M square, it's delta M square over energy. And now we are talking about 2.5, 10 to the minus 3, maybe for GeV, so that's 10 to the 9 electron volts. So if you just do this, 2.5, 10 to the minus 12 EV. And now we're getting close to that. If you're a little bit more careful, you can actually write your Hamiltonian accounting for these terms and the matter potential. So let's put the 0 here, delta M square, 2, 1, delta M square, 3, 1. That's your free Hamiltonian. And you can add your matter potential. And this will be clear in a second. Oh, man. Where is the dagger? OK, I'll put the dagger in a second. I'm writing this in the mass basis. But again, I told you that the matter potential acts on nu E. So I need to change from nu E to mass basis. I do that by plugging in PMNS matrices. One of them should be a dagger. I'll put them on one side. Hopefully it's right. That's an exercise that I did not write. You should check which one has a dagger. It does matter. If you put the dagger in the wrong place, you're going to get everything wrong, right? So I'm making a joke, but it's super important. On those notes there, it should be clear. More importantly, it should be right. All right, so, oh, I actually have written here. Yeah, this is right. So that means that your matter potential is relevant whenever is of the same size as delta m squared over 2e. You can be a little bit more precise here, and there is always like a cosine of some mixed angle that will show up. So usually, if you look for solar neutrinos, it will be the delta m squared 2, 1 and theta 1, 2. But if you're looking at atmospheric neutrinos, that will be 3, 1 and 1, 3, and so on. Sorry? Well, it depends where you write, right? The base you're writing. So so this means that this guy, because it's diagonal, this means that I'm working on the mass basis. I can always change the flavor basis by saying that the Hamiltonian in the flavor basis is U dagger Hamiltonian in the mass basis. Let me put a 0 here for the mass basis. U. And if you do that, then now you have U dagger, mass is U, and then this will be diagonal. No, I think this is fine, right? Is it? Let's see. In the flavor basis, I should have this, right? Sorry, in this guy here. Is that right? Yeah, I think that is right. Which means that my potential, so let's write the flavor potential in the mass base, I'll be very clear here, should be PMNS flavor potential in the flavor basis, the potential in the flavor basis, U dagger. So it should be this, right? Because I'm writing everything in the mass basis. We should cross-check. We should cross-check. And it's an important cross-check. Now, again, I don't know how to do things with 3 neutrinos because equations are real complicated and messy. But 2 neutrinos is great. Even I can solve 2 neutrinos. So if we do 2 neutrinos, we take one of these guys out, we take one of these guys out. The U's are just cosines and sides of the same angle. And you can actually show that, let me be a little bit more explicit. 2 neutrinos, you have this, all right? And then you have, your U, V0, U dagger, where U is cosine, sine, minus sine, cosine. I can always diagonalize this Hamiltonian to find the eigenvalues and eigenvectors. The eigenvalues of the Hamiltonian are the energy levels. So that is the energy levels on matter, accounting for this. When I do that, I can always write this Hamiltonian, the matter Hamiltonian, oh man. Yeah, the full matter Hamiltonian, I can write this as this. Let me just put a tilde here, where the matrix that I use to diagonalize this thing, HM, is, let me call some V, oh man, V is bad. U tilde, H, U tilde, dagger. Okay? So I'm just diagonalizing this thing, and you can show for 2 neutrinos, you can actually show that your mass splitting goes like A to A, and I'll tell you what A is in a second. Cosine of 2 theta, delta m square, where A is 2 energy potential. So the mass splitting here becomes this, and you can see that if A is 0, this term is 0, so if there's no matter potential, 0, 0, it's just the delta m square, so it's in vacuum. And the mixing angle, it's easier to do that for the tangent. Tilde will be like delta m square sine of theta, there's a 2 here, divided by delta m square cosine of theta, 2 theta. minus A. Now, why am I writing that? So what I'm saying here is that when neutrinos traverse matter, effectively, their mass splittings change and their mixed angle change. If matter is like subleading, that is, if this potential is smaller than these kind of quantities, you have a small change on the mixed angle and the delta M square. But if the potential is actually of that order, there is something that shows up here in the mixed angle. If you look in the mixed angle, there is a delta M square cosine 2 theta minus potential. That means that if the potential is identical to this will be a 0. Tangent going to infinity, that means the angle becomes 45 degrees. So even if you start with a small mixing, if you have enough matter, you can actually bump this mixing up to maximal and have huge oscillations there, okay, because of matter. This is actually pretty important for solar neutrinos and for atmospheric neutrinos. For atmospheric neutrinos, there is actually a resonance right where we can measure that may allow us to tell the sign of this delta M square. So this delta M square, for 2 neutrinos is kind of boring, but for 3 delta, I could have, let's say, nu1, nu2, and nu3. I could have nu3, nu1, nu2, and in principle, I could have other configurations. The reason why nowadays we know that neutrino 1 is lighter than neutrino 2 is because we have seen a matter effect that only works if this delta M squared 2,1 is positive. So delta M squared 2,1 is M2 squared minus M1 squared. Positive means M2 is heavier than M1. So we can only know that by measuring matter effects, okay? And this, in some senses, is a bit of a trivial statement that in a system of 2 levels, you're only sensitive to the difference of energy. And it doesn't really matter if it's positive or negative. It's just the modulus of the difference of energy. For 3 neutrinos, you can see more than that, but it's actually very, 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 very hard. The best way to see it is with matter effects. Let me see if I'm thinking I'm out of time, right? Is there any questions or comments? It's not just for solar neutrinos, but solar neutrinos, it is the only observation that we have where matter effects played such a crucial role that allowed us to say what is the sign of the delta M square. Because the effect is big, very big. Because there's a lot of matter in the sun. So, okay, so if I do this in the sun, let me put here G Fermi electron density. The electron density in the core of the sun is about 150 times the Earth electron density, or let's say between 15 to 150, the density of electrons on the Earth. And the sun is actually a much more rich system. Maybe I'll talk about solar neutrinos in the next lecture. I think that's a good point. So this electron density is huge, and this delta M square in the sun, well, that's what nature gave us, is 7 10 to the minus 5 eV square. So it's a smaller delta M square, which makes this more relevant. So it turns out that in the sun, the matter effects actually are so big in the sun that it's a bit tricky to say that we actually saw neutrino oscillations from the sun. I'll get more deeper on that on the next lecture, but technically we did not really observe oscillations for solar neutrinos. We observed a adiabatic transition of averaged out oscillations. So if you just take sine square 2 theta, sine square delta M square L, whatever, If this oscillates very fast, this goes to half. It averages to half. So you see a probability that's like half of an amplitude. Can you tell that this is really oscillation? I mean, at least it's a bit of grammar, right? But to me, oscillations mean that you can actually see a non-trivial evolution of the system. In principle, if I produce a system to you, which is neutrino 1 and neutrino 2, incoherent sum, you'll get half of that. So I could have gotten half of that even if nature was not quantizing, right? So that means that, to me, I can only see what I, myself, consider as oscillations if I see this phase evolving. And on solar neutrinos, we actually don't see that. But I'll cover that maybe in the next lecture. Oh, sorry. So what you see is not the oscillation inside your experiment itself, because the baselines are ginormous. So even if the experiment is inside this room, that's 0. But what you do, for example, in experiments like NOVA, where we have at Fermilab, we have a near detector at a baseline of 1 kilometer and a far detector at 800. In that near detector, you see approximately 100% mu neutrinos. At the far detector, almost no mu neutrinos. Now, these are 2 points in an oscillation curve. Of course, you do see some energy distribution, which allows you to kind of draw the oscillation curve there. So you do see this as a function of energy up to some extent in lab experiments. You do not, so L is just either 0 or whatever you did to get oscillations, but you do have some energy distribution that you can see the phase varying.
Can you talk a bit more about the labeling 1, 2, 3? It seems very arbitrary to me.
Yes.
You and I agree on 1, 2, 3.
Yes, that's actually a great question. Should never take anything for granted. Just because I said neutrino 1 is neutrino 1, that's my neutrino 1. Maybe it's not your neutrino 1. But there is one thing you can do to make this labeling physical. Do I have my PMNS here? No. So I'll just do this and then I'll finish. When you have your PMNS matrix, now, we can only do this now. In the early days, life was very hard. Let's not go there. But now we know that this element, let me do this, because then I don't need to worry about phases, and I actually know the values on the top from the top of my head. This element is about 0.6-ish, this one's 0.4, and this is about 0.02. And they should add up to 1, but, you know, approximation. Which means that, and again, this is U alpha I. So this is E mu tau flavor. And this is neutrino 1, 2, and 3. So what I'm defining as nu 1 is the neutrino that has the largest nu E admixture in it. Nu 2, the one in the middle, and nu 3, the smallest. That is a physical definition, and it doesn't matter what we agree or not. Experimentally, I can always go back and say, this is actually solid. If you start changing definitions, you change the delta M square, you change the mixing angles, you mess up the parameterization, you should not do that. But there is a physical reason why we call nu 1, and so on and so forth. Can I take more questions, or should we? All right. Yes. So it is not, minor is a tricky adjective because minor what, right? For example, the Dune experiment, it will definitely see the matter effect. Like, if you don't account for that, you actually will not be able to describe the data. In T2K and NOVA, although NOVA cannot establish the existence of matter effects itself, and the matter effects on T2K are very small, you actually can only compare their data if you account for matter effects. If you do not, their data will look weird. Their combination will look weird. So that's an argument for it's not minor, it's actually major. But we have not really observed matter effects for real except for solar neutrinos. The only observation of neutrino physics that really require matter effects alone to be explained is solar neutrinos. No other observation require matter effects. In MINOs, matter effects are like a 3–4% effect. The error bars are 10%. In T2K, they are essentially negligible. In NOVA, they are there for the NUMU to NUI, but if you don't account with, if you like, in principle, if you take them out, you also get a good fit. So it's a bit surprising that actually we have not really observed matter effects that much. Even for atmospheric neutrinos, if you put neutrinos oscillation in vacuum, you kind of get a not so bad explanation of atmospheric neutrinos. So atmospheric neutrinos have not determined the existence of matter effects at, say, 5 sigma. You have determined it at 2.5 sigma only. So that's why some people say it's minor, right? But in the future, matter effects will be larger than the effects, the error bars that we are going to get. So if you don't account for that, you're dead. Now, we do know matter effects pretty well. There's electroweak physics, so there's no, tricky part of the calculation. And the uncertainties on the density of the Earth, they're actually not that large. I mean, matter effects is not a big effect. And if you have an uncertainty, even of 10% on a small effect, that's tiny. So because of these things, it's kind of, you got to put there, but it's okay. It's not like you need to spend your nights on it. But yeah, I think the experiment that will measure matter effects for real is Dune. Even IceCube. IceCube has not really measured matter effects. It's a bit tricky because IceCube saw the absorption of neutrinos, but that's not matter effects, that's a cross-section. At the region where IceCube could have seen matter effects, it's not sensitive enough to see it. So it is very surprising that matter effects are so hard to measure. Although, again, they're super small, right? I had written somewhere. They're super small, so. All right, cool. Should we wrap it so that people can eat?
Yes, thank you. So before we go to it, yes, we have a half an hour discussion